Okay, welcome back to ChemDoctor, and this is the second video in the series on thermochemical equations, and this goes out to those hard-working general chem students that are up there in Flagstaff and to Tanner D. And what we're going to do in this video is we're going to start using a balanced chemical equation to do thermochemical calculations. Now, for this particular reaction, we're combining propane. We're actually combusting propane, which is a typical fuel that's used for barbecue grills. It's also used in home heating, in remote areas where natural gas is not available. And usually out by a house, you'll see a big round tank, and that's a propane tank. When you combust propane with oxygen, we produce carbon dioxide and water vapor. This is a classic combustion reaction with a hydrocarbon, so that the products are always carbon dioxide and water. And in addition to the carbon dioxide and the water, we also produce about 2,221 kilojoules worth of heat for this particular reaction. Now, in the last video, what I did was I talked about the fact that the energy released in a chemical reaction is directly proportional to the balanced equation. So in other words, if we burn exactly 1 mole of propane with 5 moles of oxygen, and we produce exactly 3 moles of CO2 and 4 moles of water, assuming the reaction goes to completion here, then this reaction will release 2,221 kilojoules worth of energy. All right, and to review a little bit, we drew an energy diagram for this, which you can do for all chemical reactions, I think, in general. All right, where the reactants start at some energy. We have an initiation energy, which is this hump in the middle. To get the reaction going, we go from the reactants to the products. This value here is H1. All right, if we draw the line over, this is H2. If we come out like this and we figure out our gap, which is going to be delta H is equal to H2 minus H1, that value is minus 2,221 kilojoules for this particular chemical reaction. And this reaction is exothermic, meaning that it releases energy. And again, if you're standing next to the barbecue grill, it's pretty clear what an exothermic reaction is. You can feel the thermal energy coming off of the grill as the thing is running. So the human perception is, oh, that feels warm, or that is hot, and on a cold day like it is today, raining here in Phoenix, or snowing up in Flagstaff, that energy that's being burned is what's keeping us warm on the inside of our houses. All right, now let's go ahead and start using these reactions to do calculations. So a standard propane tank that you use for these grills looks something like this. All right, and basically this thing holds about 5 gallons of gas. All right, 5-gallon tank. All right, and in a 5-gallon tank, there's going to be about 20 pounds of propane, which is an inconvenient for the chemist. This is an inconvenient amount of material, because we don't think in pounds, we think in grams, so that we can get to moles easily, right? So we need a conversion here. Remember that, or look it up if you don't remember, but 2.2 pounds, all right, and I'm not even sure if this is the right designation for that, but it doesn't really matter. 2.2 pounds is equal to 1 kilogram. All right, so if we have 20 pounds of propane, that basically translates into about 44,000 grams of propane. Okay, 44,000 grams of propane. So what I want to calculate here is how much energy, what is the total energy capacity of a 5-gallon propane tank? How many steaks can we cook, right? We're not actually going to figure out how many steaks that we're going to cook, but we're going to calculate the total energy available, the total enthalpy available if we burn all of the propane that's in this 5-gallon tank. So how do we do the calculation? All right, so we use standard theoretical yield calculations to figure this out. So we've got 44,000 grams of propane. So I'm going to put my label in here, C3H8. All right, and first thing we got to do is get to moles. So we're going to use unit multiplier method to do that. And the molar mass of propane is about 44 grams per mole. We're going to back of the napkin this thing all the way through. All right, so it's going to be 44 grams of C3H8. Putting my labels in, unit multiplier method, it's really important to put all the units and all the labels. All right, so let's see. This is going to equal about 1,000 moles of C3H8. All right, now I'm going to move that down here so we have room. So now that we've got this thing in the moles, how do we figure out how much energy is released? All right, now we need to go back and think about what this value means. All right, this is the amount of energy that's released when we burn exactly 1 mole of C3H8. So this is the energy. I'm going to rewrite it here. Minus 2,221 kilojoules of energy is released per mole of reaction. All right? And so in 1 mole of reaction, all right, we burn 1 mole of C3H8. So we're going to release a minus 2,221 kilojoules of energy per mole of C3H8. All right? So we can take the energy released per mole now of C3H8 propane. All right, and just rewrite it, mole C3H8 times, all right, and we got 1,000 moles. And you can see this value's over 1. It nicely cancels out, and what we end up with is a negative make sure I get all the right zeros in. This is a big value. All right, so it's going to be, whoops, I need, that's a comma, and here's a comma. So it's going to be 2,221,000 kilojoules of heat energy is available in a 5-gallon tank of propane. That's actually a lot of steaks. And you know, when I buy one of these 5-gallon tanks, they tend to last for you know, a home that's barbecuing. Not that often, but you know, maybe once a week, let's say. Well, that tank's going to last many months before the thing runs out. All right. Now, with that, I'm going to close, and in subsequent videos, we'll look at doing similar calculations, but utilizing the other components in this reaction, so that we have to mess with the coefficients. All right. And with that, I'm going to go ahead and close.